Hello everyone, my name is Yifan, a PhD student from University of Bristol. My research aims to investigate the orientation effects of fracture behaviors of octet-truss lattices. Both experimental and numerical methods were used in this research. First of all, I will introduce the background of this research. Periodic lattice structures have a high potential for use in modern industries, such as medicine, automotive, and aerospace. In general, the macroscopic mechanical properties of lattice structures are mainly related to load collectivity. Stretching-dominated lattices are lattices with high load collectivity, like octet-truss lattices, generally exhibits higher strength-to-density ratio than the bending-dominated lattices, so octet-truss lattice is one of the good solutions for lightweight structural applications. Studies have shown that lattice structures in different orientations also exhibit different mechanical properties. The elastic modulus, tensile strength, and fracture toughness of lattice highly dependent on the orientations. However, there are few studies on the effects of different orientations on the fracture properties of octet-truss lattice structures, especially in experimental study. In the present research, the orientation effects on fracture behaviors of octet-truss lattices were studied by experimental and numerical methods. Compact tension fracture specimen was used to study the fracture properties of octet-truss lattices in different orientations. The lattice samples printed in three orientations, referred to as orientation X, orientation Y, and orientation Z, as shown in Figure 4. The cell orientations are defined by loading direction and the local coordinate of unit cell. For example, the orientation X specimens, the x-axis in the local coordinate system is parallel to the loading direction. The dimensions of the CT specimens were designed according to the ASTM standard. Octet-truss lattices in three different orientations were manufactured by the SLA printing technique because SLA printing has high printing precision and can print smooth surface. Figure 5 shows the printed octet-truss lattice samples. The designed nominal radius of the struts is 0.5 mm and the nominal length is 5 mm. The geometry of the specimen is large enough to achieve a high ratio of W to L in order to reduce the surface effects. The material properties of parent material were measured first using dog bone specimens based on the ASTM standard. The dog bone specimens were manufactured using the same process parameters as the CT specimens. Tensile tests were performed using an instrument test machine. Displacement control was used with a rate of 1 mm per minute. It is known that the mechanical properties of 3D printed photopolymer are related to the printing direction. In this research, specimens in two printed directions were used, namely the vertical printed and the horizontal printed specimens. Three specimens in each printing orientation were tested using the same test conditions in order to assess the scatter of the results. The strain was measured by a 10 mm gauge length extensometer. The engineering stress and strain curves of the 3D printing photopolymer are shown in Figure 6. The 3D printing photopolymer showed a distinctly brighter performance, and the specimen failed at a relatively small strain under tensile load, and the moduli and the ultimate tensile strengths are obtained here. Fracture tests of different orientations lattice specimens were carried out, also used instrument test machine with displacement control of 1 millimeter per minute. Two specimens were tested for each orientation. A camera was used in the tests to record the deformation process of lattice specimens in three orientations. The displacement and the reaction force of the loading crosshead were recorded during the experiments. The fracture response of octet-truss lattice in different orientations was simulated by ABAX. Each strut is meshed by using beam element B31. Each strut was meshed by 10 elements to provide convergency numerical results. The explicit dynamics procedures were used to model the quasi-static process, and the geometric nonlinearity was taken into account. An element deletion method was used to model the strut failure in tests in order to obtain the crack path, and the mechanical properties of material were obtained from the above tensile tests, and the properties for vertical painted photopolymer were used for orientation X lattice, and horizontal painted properties were used for orientations Y and Z lattices. And the two controlling points defined at the hole center were coupled to the motion of loads around each pinhole. Displacement was applied on the top controlling point in the vertical direction, and the controlling point and the lattice bottom part was constrained over all degrees of freedom. The load displacement curves of octet-truss lattices in different orientations are shown in Figure 9. It can be seen that the photopolymer octet-truss lattices exhibit distinctly brighter performance. Once the load reached the critical value, fracture occurred and specimen failed. The fracture resistance for octet-truss lattice is calculated according to the ASTM standard. Geometrical values of lattice specimens in different orientations are shown in Table 1. Substituting the critical loads we obtained and the geometrical values into equals 1 and 2, stress intensity factors and fracture can be calculated. Photographs of the lattices taken during the and after fracture for different orientations are shown here. The fracture in different orientations lattices initiates and the struts adjacent to the crack tip. Once the first strut failed, the specimen quickly broken into two pieces. Most failures in struts occurred at this location near the joint, caused by the influence of local stress concentration. The crack passes for orientations X and Z specimens were almost horizontal to the initial crack, while the crack of orientation Y specimen deviated from the initial crack, and the entire crack plane was rotated by 30 degrees to the initial crack plane. Figure 11 illustrates the mechanical responses of lattice structures in different orientations. The displacement and reaction force data were obtained from the reference point coupled to the nodes around the top pinhole. It can be seen from the Figure 11 that the numerical results are in good agreement with experimental results in all three orientations, except that the predicted displacements when specimens failed are a little larger than the experimental results. The numerical crack paths of octet-truss lattices in different orientations are shown in Figure 12. The numerical simulation predicted the crack initiation and propagation in lattices in all three orientations. The predicted crack paths for orientations are consistent with the experimental results shown in Figure 10. All the struts in lattices failed at the location near to the joint. In simulation, the same as the experiments. Here is the conclusion of this research. The fracture properties of octet-truss lattices in different orientations have been investigated experimentally and numerically. In this research, the fracture resistances of printed photopolymer lattices in orientations X, Y, and Z are obtained here. Lattice orientation has significant effects on the crack passes. For orientation X and Z specimens, the crack passes are horizontal to the initial crack, and the crack or orientation Y specimens deviate from the direction of the initial crack with the angle of 30 degrees. The simulation results using beam elements have good agreement with experimental results, both in terms of the mechanical responses and crack propagation patterns in all three orientations. Thank you. Any questions?